The ultimate form of both AR and VR in the long run lies in a post-HMD era. It is only through this avenue that the total breadth of XR's promise will be fulfilled. Here I will discuss the distant future of this technology and the form factors that will eventually provide XR beyond glasses and head-mounted displays. I'll begin with nearer-term prospects like contact lenses or optic nerve implants and explain how they can offer new use cases beyond which HMDs are capable of providing. Following that, I'll begin discussing brain-computer interfaces and proceed to illustrate their unrivaled capacity to serve as the highest manifestation of this technology. To begin with, AR contact lenses already exist, albeit in a primitive form. The first publicly demonstrated working AR contact lens was developed by Mojo Vision, a startup founded with the sole purpose of creating the world's first AR contact lenses. In June of 2022, that goal was finally realized when Drew Perkins, the company's CEO, wore a functional prototype of the device. This prototype, however, is only capable of AR in the most rudimentary sense of the word. It can only display single-color green text that is fixed to your head movement, a far cry from full AR headsets that can mix positionally tracked holograms into your view of the world. Ultimately, due to the way that your eye perceives light and the proximity of the display to your retina in such a device, there may be inherent limitations to how rich an AR experience contact lenses can ever offer. Because of this, it's likely more feasible to simply enable full AR through an optic nerve implant. Through this approach, we are less limited by the laws of physics, and the fundamental technological foundations to create such a device already exist. It is more a matter of just improving our understanding of how the brain processes electrical impulses and converts them into visual imagery. Due to the very nature of how such a device would function, it would allow AR and VR to seamlessly converge, permitting the user to switch between the two on a whim. But perhaps the most salient consequence to ensue from the development of this technology would be its implications for VR rather than AR. However, for the sake of a smooth transition, I'd like to continue with AR first due to all of its use cases I've already listed. In effect, the way an optic nerve implant would function is fairly straightforward. We could send visual information encoded in electrical impulses to the brain itself, in the same way that your brain processes these signals via your eyes and creates an image out of them for you to see. By doing this, we could create AR that encompasses your entire peripheral vision and is visually indiscernible from reality. Anything about the world around you at this point could be visually manipulated on demand. Say the sky is gray and cloudy. Through the use of an AR filter, you could make it look totally sunny and blue. Or maybe it's late fall and you don't like the way the trees look leafless and barren. You could make it so they appear to be covered in leaves. Or perhaps you don't like the paint color your family decided on for your walls. You could simply make it so that you'd see the walls in a different color. Whereas they decided to paint them white, you could choose to see them as red, blue, or any other color of your choosing. Though at this point, why paint walls at all when anyone could see anything however they wanted to? This would also translate over to how you see other people and how they see you. For instance, anything about the physical appearance of you or others could be altered at any given time. Why dye your hair anymore when you can make it appear any color you want others to see it as? Or why wear makeup or use nail polish? To elaborate even further on just how far this could be taken, let's say maybe you're not happy with your height. Anyone could use an AR filter on themselves that allows them to adjust how tall they look to others. From changing your eye color to using a muscle filter to make your arms appear more brawny. The amount of ways this feature could be applied are nearly limitless. You could even make yourself appear younger in spite of your actual age. By using a filter that de-ages you, similar to CGI used in movies, you could get rid of any visible wrinkles or skin sag. You or anyone else could make yourself look as young as you want, regardless of how old you are. Obviously, these kinds of AR filters would be exclusive to optic nerve implants or contact lenses. Glasses would be impractical for this set of use cases for two reasons. One, when you take them off, the AR layer over people and things would immediately cease to exist. Due to this, nobody would stop dyeing their hair or making cosmetic changes when those alterations are only visible through glasses that can be taken off at any time. And two, glasses don't encompass your entire peripheral vision. In essence, this means that only within the range of their lenses could AR be displayed. The result of this being, if you moved your head to such an angle that someone no longer fits inside the lens frames, the illusion would be broken. For these reasons, only a retinal implant or contact lens type device could aptly make use of this feature. As I said earlier, the way this technology could integrate AR and VR into a single device has dramatic implications. Currently, VR relies on head-mounted displays which are large, heavy, and unable to provide an FOV commensurate to your natural human field of vision. For those who haven't used a VR headset, the perceived image one sees appears similar to the view that you get through a pair of binoculars, only with a substantially larger field of view. While this can offer some very compelling experiences, in no way would someone mistake them for being real due to this limitation. However, by leveraging the optic nerve, we could send electrical signals directly to the brain, creating a VR experience that covers your entire peripheral vision and is visually indistinguishable from reality. This would eliminate the need for bulky headsets and offer unparalleled immersion. The utility that this type of experience could offer, combined with the lack of friction to use it that it could provide, like not needing to wear an HMD, would open up entire new use cases. For example, while current 360 photos and videos viewed on a VR headset fall short of convincing realism, by transmitting their visual information encoded in electrical signals to the optic nerve chip, we could produce an image that's impossible to discern from reality. Imagine having the ability to pull up a virtual screen in front of you containing all of your photos, and then by simply tapping on one, being able to re-enter that exact moment on command. So far as your eyes could tell, it would appear like you were actually there again. You could turn around or look in any direction, and whatever was there at the time would have been captured and part of the photo. And by using your brain itself to render the image, you'd see it with a field of view and resolution equal to that of normal human vision. This would be the closest thing to time travel that is physically possible. Any moment in your life could be viewed again in a way that appears visually identical to when it actually occurred. From the most memorable moments in your vacations to when your child was born. Any event you deem worthy of documenting could be revisited if captured with a 360 camera. You could also share these photos and videos on social media, allowing anyone to view them if they desire, similar to how we share 2D media today, only they could see the exact moment you shared in a way that looks equally as real as when it truly happened. But why stop there? Once this technology is possible, 360-degree capture will become the dominant way of capturing photo and video. For this reason, visual media on the internet will largely consist of this content. This would allow you to look up any event in recent history and by the tap of a finger, visually revisit that moment. This would function in the same way that we can currently Google past events and see 2D photo and video of them. From historical speeches to images from wars, the full gamut of history could be archived and available to re-witness like you're actually there. Of course, only photo and video captured with a 360 camera would be viewable in this manner, most of which wouldn't have been, before VR via optic nerve stimulation warranted such a transition. Because of this, the amount of 360-degree photos and videos available to view prior to this technology's existence would be limited, but post this transition, anything of historical significance could be captured in this way. This is similar to how events that preceded the advent of cameras were unable to be documented via photography, and thus are only viewable as visual recreations and paintings. All in all, the transition from 2D photo and video to fully immersive 360 content will represent a change even more seismic than the shift from paintings to 2D photo and video. Obviously, this wouldn't just be limited to historical events. Almost anything on the internet could be viewable in this way. Say, for example, you look up Mount Everest, and a virtual web page with dozens of photos of it appears. By tapping on an image, its contents would visually replace your surroundings, and you'd immediately feel like you were at the location of the photo. In addition, this technology will fundamentally transform the way we consume news media as well. Imagine sitting in your living room when the nightly news comes on, and having a hologram of the anchor appear in front of you. After starting off by briefing you on all of the major events of the last 24 hours, they could say they're taking you to the scene of their first story. Currently, this involves showing 2D footage of reporters at the site of the news source. Only with this technology, they could make it so you'd physically feel like you were there. Your room around you would disappear, and it would look as if you were in that exact location. As far as your eyes could determine, it'd appear like you were present at crime scenes, war zones, or any number of different places in a way that's 100% true to life. This would also change how we experience live events. Anything from the Super Bowl to concerts to presidential inaugurations could be viewed in a way that's visually indistinguishable from physically attending. All of these use cases serve as an impressive testament to this tech's revolutionary potential. But what if we didn't just stimulate the optic nerve? What if we took control of the entire sensory apparatus within the brain itself? A direct neural interface would not only enable us to bypass the eyes and have full control over our vision in the same way an optic nerve chip would, but would in effect allow us to change everything about how we perceive reality itself. Currently, two types of brain-computer interfaces exist, ones that read information from the brain and ones that write information to the brain. But I'll start with the former, as it's likely that a mainstream iteration of it will be created first, since a version that can offer compelling use cases could potentially be achieved non-invasively. Even so, the current state of the art for both requires invasive surgical implants. Eventually, this is likely to change for BCIs that read information from the brain, but due to how BCIs that write information function via direct brain stimulation, it's likely that they will always necessitate some level of invasiveness, though the avenue through which that is achieved is likely to eventually rely on things other than surgery by the time they become widely adopted, which I'll discuss later. As of today, there are different types of BCI systems that read information from the brain, but the most accurate involve placing electrodes directly on it to record its activity. This allows brain signals to be detected and then processed using algorithms that extract relevant information, like the user's intention to move a particular body part, for instance. This can then be translated into commands that can be used to control external devices, like how this woman moves a cursor and selects characters with her mind in this video. While this technology is useful today for people like this woman with ALS, it is orders of magnitude slower than we can type with our fingers on a phone or physical keyboard. Eventually, however, instead of moving a cursor with your mind to select individual letters, future iterations of this technology will allow you to think full words or sentences in your head and have them converted into text. This would allow you to type at the speed of thought and in effect function as a kind of silent speech interface. This technology, alongside an optic nerve chip or contact lens type device, or eventually a BCI that writes information directly to the brain, which I'll elaborate on later, would replace touch as the primary form of human-computer interaction. You could simply think any question in your head, and a virtual screen containing the answer would appear in front of you. This could also enable a form of virtual telepathy. By producing text just by thinking words, you could type out a text message entirely with your mind and send it to someone. After they receive it via notification augmented in their field of vision, they could open it up by simply looking at it and then generate a response via the same method of input, allowing two individuals to correspond with each other by thought alone. Not only will this technology replace virtual QWERTY keyboards as the primary method of composing text, but it will in large part render touch obsolete for other purposes as well. Take the way we interact with web pages, for instance. Today, when you're reading an article on your phone, once you reach the end of the amount of text that can fit on your screen, you scroll down with your finger to make more visible. With a BCI, it would instantly detect once you finished reading the last observable paragraph and automatically scroll down for you. These are just a couple of the many ways BCIs can fundamentally reshape the way we interact with technology. But the use cases I listed pale in comparison to what a neural interface that could accurately write information to the brain could unlock. As I previously noted, it could essentially allow us to alter everything about our perception of the real world, and at the same time, also enable us to reach a level of immersion in VR that is indistinguishable from reality on every level. This type of application, among others which I'll get to, will require BCIs that can write information to the brain with a high level of precision. And as I mentioned earlier, any system capable of this is likely to be invasive. When I say invasive, however, I mean so only in the strict sense that it will require direct interaction with the brain, because of technology like nanobots that could allow us to achieve this without surgery. Through a simple injection, nanobots could be inserted into the capillaries, allowing these microscopic devices a direct pathway to the brain. These nanobots would then autonomously navigate towards specific neurons responsible for various senses, like touch, smell, vision, and hearing. One way this technology could be applied is by enabling virtual reality from within the nervous system. When a user desires to enter a fully immersive simulation, the nanobots could promptly position themselves, suppressing the signals your brain receives from your real senses and replacing them with signals corresponding to the virtual environment. The BCI would then capture a person's intentions to move their limbs by monitoring motor-related brain activity. In response to their intended movements, it could generate corresponding actions within the simulation, allowing them to move about and interact within the virtual environment. In effect, the user would enter into a dreamlike state, leaving their real body stationary and shutting out all senses from the real world. Because of how such a system would transmit electrical signals directly to the brain, it would allow the brain itself to generate the visual experience, in effect making it the GPU, essentially mimicking the way we dream and using only your brain to generate the graphics. Obviously, Once the technology that allows fully immersive VR is possible, it could be utilized for other purposes as well. Since we'd already have the ability, by default, to manipulate our entire sensory apparatus, this could also be applied to AR. Not only could you simply call someone by thinking about it and have them appear in front of you, but you could shake their hand or give them a hug and interact with them as naturally as if they were actually right there with you. To achieve this level of telepresence, the DNI would interface with various components of the human sensory system, including vision, hearing, and touch, much in the same way fully immersive VR would function, only it would be adding things to the real world as opposed to shutting you out from it. Another byproduct of this technology would be the obsolescence of devices such as screens, headphones, and speakers. The BCI could process audio data, which would encode it into neural signals that mimic the patterns generated by the user's brain when perceiving sound. These encoded signals could then be sent directly to the relevant auditory regions of the user's brain. Once the encoded audio signals reach these parts of the brain, they'd be interpreted as sound. This would effectively allow the user to perceive audio without requiring headphones or speakers. Physical screens would already have been long obsolete before this, as an optic nerve chip could have achieved such a feat well before we actually begin tinkering with the brain itself by stimulating the visual cortex. Moving past XR-related features, BCIs also have the potential to upend traditional education as we know it, by allowing you to directly download information into your brain. This has already been achieved in experiments with mice. One of the studies I'm referring to involved 2 mice with electrodes implanted in their brains. One of the mice was taught to go through a complex maze, effectively encoding the memory of how to navigate through it in its head. The other mouse had never been through the maze, but upon transferring the memory of how to do so from the one mouse's brain to the other, it instantly knew how to get through the maze with no prior training. Scientists have been able to replicate this for the transfer of other types of memories as well. By applying this to humans with future technology, this could eventually allow us to download skills and knowledge directly into our brains. For instance, imagine being able to simply download a new language and instantaneously know it. Or instead of reading a book for the purpose of obtaining information, you could simply download and store all of its relevant facts in your brain so that you can always instantly remember and retrieve them on demand. This could encompass a wide range of abilities and eventually make school and traditional forms of learning obsolete. Another profound way this technology could be employed is by totally blocking your ability to feel pain. This would involve intercepting pain signals at various points along their neural pathways and halting their transmission. By integrating sensors into the nervous system, the DNI could detect pain-related electrical activity and apply a counteractive stimulation to neutralize or suppress the pain signals before they reach the parts of your brain that process them. In doing so, this would totally rid the human experience of pain and confine the sensation to history. Obviously, this could pose a challenge in terms of detecting health issues and injuries. However, such a system could be designed to alert you about potential problems even if you don't directly experience pain from them. For one, it could allow users to set specific thresholds for criteria or alerts. For example, you could set it to notify you if your heart rate exceeds a safe level, or if there's a significant change in your body temperature. This way, you could be alerted of health issues even in the absence of pain. After all, by the time such advanced BCI technology is widely used within the general population, it's likely that other forms of technology will be integrated within the human body as well, for the purpose of health monitoring. These devices could continuously collect data, and deviations from normal ranges or specific patterns associated with health issues could trigger alerts. Similarly, this tech could also be used to modify our perception of temperature as well. The DNI could transmit specific electrical signals to the neural pathways responsible for temperature perception. By selectively stimulating or inhibiting these pathways, the DNI could modulate the brain's interpretation of temperature signals, leading to a perceived change in temperature. As an example, say you're in a room that is uncomfortably warm. You could simply adjust the way your brain perceives the temperature accordingly and make it feel as cool as you want. This could also function the other way around and make cool environments, both in or outdoors, as warm as you desire. As you can see, the applications for this technology are essentially without limit. Anything about ourselves or the way our brain processes sensory information could be altered. Take fear, for instance. The part of our brain associated with fear-related processes, the amygdala, is what is responsible for this feeling. A direct neural interface could be used to totally eliminate the sensation of fear. Or if you didn't want to eliminate it in its entirety, as it may be useful in certain situations, it could filter out and remove fears you have of specific things you're afraid of, like the fear of death or arachnophobia, for instance, or if someone's scared of heights or afflicted with social anxiety. These fears, along with any others you can imagine, could be eliminated. To achieve this, the neural interface can employ algorithms that analyze incoming neural signals and identify patterns indicative of fear responses. These algorithms would be trained to recognize and distinguish fear-related activity from other neural patterns. Upon detecting this fear-related activity, the neural interface could apply specific electrical interventions to modulate the neural signals. This modulation could involve inhibiting or altering the transmission of fear-related signals in order to suppress the sensation of fear. Another useful application for advanced BCIs could be influencing our perception of time. Accounts of people experiencing this phenomenon have been widely reported when under the influence of psychedelic drugs, and it's obvious that the ability to precisely tailor this to one's needs could be very useful in certain instances. By manipulating neural activity in regions associated with time perception, like the prefrontal cortex, the interface could create the illusion of time dilation or contraction. This would let us change how we subjectively experience any given amount of time. An hour could be made to seem like 5 minutes, for instance, or the other way around. Obviously, this could be applied to profound effect, and I'll leave it up to all of you watching this to imagine all of the ways it could be utilized. Another application I'd like to list is hunger suppression. Today, when attempting to lose weight, people rely on various medications, exercise routines, or diet changes to varying degrees of success. But through the use of a neural interface, specific brain regions involved in hunger regulation, like the hypothalamus, could be targeted. This would effectively allow us to turn our hunger on and off on demand. Not only would this make forms of medication that facilitate weight loss redundant, but this same process could be applied to other regions within the brain and make other types of drugs obsolete as well. For instance, why take antidepressants when you can simply stimulate the parts of the brain that they target? Through targeted neural stimulation, the DNI could deliver precise electrical stimuli to specific parts of the brain implicated in depression, such as the prefrontal cortex or limbic system. By modulating neural activity in these areas, it could restore balance or enhance neural circuits associated with mood regulation. This could even be used to replicate the experience of recreational drugs as well. This could work by detecting and analyzing neural activity associated with drug-induced experiences. This could involve identifying patterns related to neurotransmitter releases or activity in specific brain regions. Based on the analyzed neural activity patterns, the interface could apply targeted electrical stimulation to specific brain regions involved in the desired drug-induced effects. With sufficient understanding of where and how to target these regions, the stimulation could mimic the changes in neural activity caused by any of these drugs. This opens up an interesting paradox, because by the time we're able to achieve this, the same technology could be used to cure addiction to begin with, or potentially even edit your desires, which begs the question as to whether this is something anyone would even want, if you could just simply make yourself not want it. And two, even if we did, why rely on mimicking the effects of current drugs when we could potentially create highs and experiences orders of magnitude more pleasurable or profound in what they can achieve? The last use case I'll list is the ability to induce sleep. An advanced neural interface could not only allow you to fall asleep on demand, but precisely control how long you wish to be asleep for. You could simply instruct it to make you fall asleep within 10 minutes and wake you up in 8 hours, for instance. This would work by the BCI stimulating areas of the brain that initiate sleep, such as the preoptic area of the hypothalamus. It could then gradually decrease the sleep-inducing signals as you get closer to the end of the set time limit you requested to be asleep for. This would allow you to initiate a wake-up process that gently transitions you back to a wakeful state. To end with, the technological undergird for all the aforementioned use cases I just listed already exist. Direct brain stimulation in humans has already enabled us to elicit all sorts of reactions from individuals. In one study, for instance, a patient with epilepsy had electrodes placed on their brain before surgery. Upon applying electrical stimulation to the anterior insula, a part of the brain known for emotional processing, the patient immediately began crying and experiencing extreme sadness. As soon as the stimulation ceased, the crying immediately stopped. Once it was reapplied, however, they began crying again. Other experiments have been able to make individuals laugh uncontrollably by stimulating a part of the brain called the cingulate bundle. A wide range of feelings have been able to be induced in individuals in experiments, from extreme happiness to a profound sense of fear. Even out-of-body experiences and auditory and visual hallucinations have been achieved through the stimulation of different brain regions, with a person in one study reportedly seeing indoor and outdoor scenes of the neighborhood that they live in. Brain chips for blind people that can reproduce vision in a primitive way have also been created. They work by taking in visual information from a camera near the eye, and then sending this information to their visual cortex, allowing them to perceive a crude outline of the world around them. This works in the same way I described how more advanced versions of this could enable both full VR and AR. I list these examples to illustrate that primitive forms of many of these uses are already possible, though only to a limited degree and requiring invasive and risky surgery. But future technology like nanobots that I mentioned earlier in this video are capable of changing that. With improved understanding of the brain, and the means to bidirectionally read and write information with extreme levels of precision, BCIs have the ability to change the world like no other technology in history. All the things I discussed today are part of a long series of upcoming videos that pertain to both the implications and use cases of advanced future technologies and the impact they can have on humanity. If you found this video thought-provoking, I'd appreciate it if you'd hit the like button and subscribe to my channel. Stay posted for new videos, and I'll catch you there.